Okay, let's continue from where it went off.
Just a minute, please. Yeah. Point 4 times what? Times 0.6. The color is not too visible. So 0.4 times 0.6, okay, plus 0.6 times what? Times 0.4. Okay. Then for the next row, once you are done, you repeat the same thing for the next row, the same estimation. So that will be so that should be for the next estimation to be 0.6, okay, times 0.4 plus, okay, 0.4. That will be this times that, okay, and then this one times this, okay. So 0.6 times 0.4 plus 0.4 times what? 0.6. Okay, then you repeat for the next column. So next column will be this times this, and then this times what? That. So that will be 0.6 times 0.6 plus what? 0.4 times 0.4. Okay. Yeah, so once you do that calculation, okay, you should get the final result which we have over here. So you can confirm, just confirm this one is 4 times 4 is 0.16, okay, and then plus 6 times 6 will be 0.36, okay. When you add the 2, that should give us what? 0.52, okay. Then when you come here to, this is 6 times 4 should give us 0.24. This is also 0.24. When you add, you get 0.48. The same way 0.24, 0.24, 0.48, 0.36, and 0.16 will give us 0.52. Okay, so that is how you do your matrix multiplication. Okay, so once you've multiplied the matrix twice, okay, based on the Kolmogorov-Chapman theory, this essentially gives us the transition of the probability of transition from states. So if you look at this, let's go back to the question. It says a computer operates in 2 different modes. Every hour it remains in the same mode. So let's say mode, we have 2 modes, mode 1 and mode 2, mode 1 and mode 2, okay. So in the same way, when it comes to the final transition, it will be 1 and 2, 1 and 2. But you are asked to compute the 2-step transition probability what? Matrix, okay. But if I had asked you to find the probability of moving from states, let's say 1 is back to state 1 in 2 transitions, okay, in 2 transitions, or in 2 hours, let me put it that way. In 2 hours means 2 transitions. For every hour we move, okay, so we transit in every hour. So if I say 2 hours, then I'm talking about 2 transitions. So state 1 back to state 1 in 2 transitions will be this probability here, okay. So technically you write that as the probability of moving from, okay, the process moving t plus what? t plus 2, okay? T plus 2 being equal to what? Being equal to 1, given that the x, given that x at t is equal to 1, will be given as 0.52, okay? So that is how you get the probability. Okay, any questions on this point? Any question on this point? Any questions here?
Okay, so okay, we are just replaying. So let me fast forward to the next example.
Okay, fine. Let me take another example. Let's go back to my clear screen. Then we can use that. Okay. So I need a clear screen then. Yeah, so let's say that the probability, okay, or let me give you the day is Friday, okay? What will be the probability? What will be the probability of moving from a sunny day, okay, I is a sunny day, to a rainy day? So let's make J to be a rainy day, okay, rainy day. That will be, today is Friday, so that will be on Sunday, or even Saturday. Let's put it that way. Good. So, Saturday is just tomorrow. Let's talk about Sunday. So that will be Sunday. Okay. So if that is the case, if we are transiting from Friday to Sunday, okay, between Friday and Sunday we have Saturday. So Friday, Saturday, and what? Sunday. Friday to Saturday will be the first transition, which is Pij. Then from Saturday to Sunday will be the next transition. Okay. So that should give us per the Pomograph, generalized form of the Kolmogorov-Chapman. That will be Pij raised to the power 2. Okay. Which is just a multiplication of the initial transition itself. So let's multiply that and see the outcome. So this will be, you need to have your calculators with you. So Pij2 will be what? We know this is S, this is R. This is 0.5, 0.5. And then we have 0.7, 0.3. Then you multiply with itself. This will also be 0.5, 0.5. This will be 0.7, and then this is 0.3. So in matrix multiplication, like we said, you multiply row and column, okay? So when you're multiplying, this will be 0.5 times 0.5 plus 0.5 times 0.7. Okay, then we go 0.5 times 0.5, okay, plus 0.5 times 0.3. Okay, then we are done with this row, so we come to the next row. That will be 0.7 times 0.5 plus 0.3 times 0.7. Okay, then we have 0.7 times 0.5 plus 0.3 times 0.3. Okay, good. So once we do this estimation, we should get, I've cleaned the original matrix. So that should give us, this gives us 0.25. Okay, that's 0.5 times 0.5. This will give us 0.35. So when we add them, that will be 0.6. Then this gives us 0.35. This will give us 0.21. When you add, that should be 0.56. 0.56. This will give us 0.25. This will give us 0.15. When we add, we get 0.4. And this will be 0.35. And the last one will be 0.09. Okay. Okay. So when we add the two, that should give us what? 0.44. Okay, so 0. Good. And then we keep the structure. The structure is the same. So this is sunny, rainy. This is also sunny, rainy. Okay. So now let's go back to the question. The question said we should find the probability, okay, of transiting from a sunny day to a rainy day within the 2 time steps from Friday to Sunday. So this is how you write it technically. That will be the probability okay, of X being on Sunday. So let me put it in simple terms for you. Okay, was rainy, given that X on Friday, okay, is what? Is sunny. Okay, so that should be this here from meaning we are moving from S to R. So this is S initially, and then this is R in the 2 time steps. So the probability we are looking for is this probability here. So that probability should be 0.40. So this is the chance that is going to rain, okay, there's going to be a sunny day on what? On Sunday, given that it's, final result is R. So it's going to rain on Sunday, given that today it is a sunny condition. Okay, so looking at the chance is quite small, right? So let's say on a real life scenario, if I was a newscaster and then I came to the television set, I'll come based on these probabilities I've estimated. Okay, I'll come to the screen and tell you there is a very little chance it's going to rain on Sunday. Okay, the probability is that is four out of what 10 chance that is going to rain on Sunday. So it's very likely it's going to be a sunny day on what on Sunday. Okay. So you can see how these things are applied in various what fields.
Okay, so that is the last part of what we did in class before the mid-semester examination. And like you can see, we only look at the end state, which means we are left with steady state, transition, and also we are left with the classification of the various Markov, okay, model or parts in the Markov model to complete module 2 of the course. But before we begin that class, I want to find out your comments. How was the mid-semester? And if there are any other comments we need to look at before we continue the next half of the course. So let me take your comments with regards to mid-semester exams, whether there were any challenges, and then we proceed to today's class. Gabriel.
Yes, sir. Good evening.
Yeah, evening. Any issues with mid-semester?
Yes, I have some little bit of help I'm seeking from you to give us one detailed use of the MATLAB to at least solve one of the questions of the midterm, so that we gain a detailed approach of the use of the MATLAB application.
Okay, we'll be doing MATLAB proper. We'll be doing MATLAB proper.
Okay, sir.
Immediately after queuing models, we'll begin with MATLAB. So you have no cause.
And also,
Immediately after our next topic, we'll be doing queuing models. Then immediately after queuing models, we'll start with practicals, MATLAB practical.
okay, sir.
Okay, any other comments?
And also, we are now about to approach that side of the slide. So I'll reserve it because there was one example in the slide that I think the probability use was in contrary with what was stated in the question, but we are now approaching. So when we approach.
Okay.
And I would like to seek for.
Please come again.
I would also like to simply said.
Yeah, come again with your question.
So I said when I was revising through the slides.
Yeah.
The one that we are currently on. Getting to the end, there was some contradictory to me of the probability that was used in contrary to the one that was stated in the question. But we are now approaching there. So when we approach, then I'll raise that issue.
Okay. That's fine. Yeah.
And I also like to request for us to be taken to the question 4 of the midterm.
Well noted.
Gabi, not only question 4, at least we should go through most of the questions, not only question 4, because I bet you most of our colleagues were not able to do the exams, to be honest.
Okay. So for your mid-semester, ideally, I'm supposed to have discussed it with you today. Okay, ideally that is what I do in the normal face-to-face. Just after midterm, we have the discussion in class. But because it is online, sometimes students have challenges here and there. And some students will appeal, okay, for resubmission here and there. So you do not want to, immediately after exams, your first class after exams, you solve the mid-semester. In case a student has a challenge and has to resubmit, and the lecturer has solved the question, then it means you've not been fair as a lecturer to the other students who submitted ahead of time. So we have to do that next week, not this week. Okay, in your own interest. So let's wait next week. By then, 2 hours, I'll finish marking. Then we spend the time, discuss the questions, discuss your scores, everything about your mid-semester examination. Good. But I'm not getting any comments on assignments, on other issues. Do you have any comments on assignments? Okay. So it looks like you're okay in that sense, in that regard. So let's continue with our state holding probabilities, which will lead us to study. Yes.
So sorry for disturbing.
No problem. No problem. Go ahead.
I just remembered when you spoke about the assignment.
Yeah.
The previous one that we submitted, we've not heard anything about it, about the MATLAB.
The assignment, you've not heard anything about it?
Yes, sir. The one we sent to your email.
Okay. Okay. You sent the files to my email, right?
Yes, sir.
Okay, so this is what you're going to do. You do me a favor, resend all your files. I'm saying resend. Those who did not send, this is not a time for you to send. Just resend all your files to me, okay, again in my email. And then next week, we'll dedicate the time to touching on all assignments and your mid-semester. I think next week's class will be dedicated to that. If there are any other issues, please let me know so that I can structure my next class before I attend lectures. Okay, so
okay, sir.
Yeah, good. The next thing we're going to look at will be steady state transition probability. That is, we looked at the M state. M state means moving 2, 3, 4 time steps. But if we have, let's say, 100 transitions, okay, you cannot keep multiplying the matrix to the 100th order. Means p raised to the power 100. You can't do that. Okay, so we call that a steady state process. Okay, good. And I'll let the video play. Then you ask your questions as usual. Okay, if you have any.
That will give you the transition. Hours, we are looking at a time a process will remain in its state until it transits. So maybe we have a customer who always want to buy Coca-Cola. Okay, yeah, we'll keep buying Coca-Cola, but eventually this customer will move from Coca-Cola drink to another drink. Okay, but the question is, how long is it going to take for this customer? How long will it take for this customer to move from the choice of Coca-Cola to another drink, let's say Malta Guinness? That is what the state holding probability is talking about. And if you look at the scenario, you clearly agree with me that this scenario is a geometric process. Okay, it's a geometric process because we are essentially talking about the probability of a phase transition. And if you remember, for a geometric distribution, we made mention that geometric distribution is about having the first occurrence, the first transition. So you have to wait a number of times before the first transition takes place. So let's see what we have here. We said, suppose that at the given point K, the Markov chain has transitioned into a state xki. An interesting question is, how long will it stay in that state? Okay, so if we let vi be a random variable, which represents the number of time steps that xk will be in I. Then if we are interested in the probability of those number of steps, okay, for the process to remain in the state I, it is going to be the probability of Vi in a certain state, or the number of steps is just going to be what? The geometric distribution, okay? But this time it's going to be 1 minus the probability of remaining in the state times the probability, okay, that is P. Let me come again. So this is the probability of remaining in the state a number of times, and then the probability times the probability of the first transition. The first transition means you are no more in the state. So it will be 1 minus the probability that you remain in the state, okay, which is the geometric process. Good. And like we said, this also have a memoryless property. So when we are modeling it, okay, you want to find how long a process will remain in the state. You model the probability using the geometric distribution. Okay. Then another aspect we also need to understand is what will be the probability of the process in the long run. So what will be the probability of the process in the long run? If somebody purchases Coca-Cola or a particular stock, okay, what will be the probability, the chance that in the long run, after years, this person will go back purchasing the same brand of drink? That's what we talk about when it comes to what? We are in the state distribution. So in state distribution here, we are talking about if you are given the initial state of the process and we want to find the probability that is going to be in that process at a particular time. What do you do? Okay. And then here, all you need to do is to solve this equation, which is pi, okay, k is equals to pi k minus 1 times p, okay, to get the probability of the state distribution. Let's demonstrate this using an example. So for example, we have this question here. It says a computer device can either be in what? A busy state processing a task, or an idle mode, which is state 0. Idle is state 0, state 2, and then busy mode is state 1. Okay, being in a busy mode, it can finish the task and enter an idle mode with a probability of 0.2.
Class, the Zoom will be going off any moment, but I'll be coming back on, okay, as usual. So take note of that.
Now, with the probability of 0.8, it stays in the busy mode. Okay, being in an idle mode, it receives a new task with any minute with a probability of 0.1 and enters a busy mode. Now, it stays another minute in the idle mode with a probability of 0.9. Here is the initial state of the process. So it says if initially the state is idle, so it says initially if your state is